Nomenclature, which of course in chemistry deals with the naming of compounds. We're just going to continue naming the compounds. Just as a reminder, we're working with ions, which are atoms that have either lost or gained an electron. Those that are positive are cations, those that are negative are anions. Anionic compounds or combinations, we'll see that there's a positive and a negative, a metal and a non-metal. When you are working with those that are monoatomic, meaning that there's a single element, all positives just carry the name of the element, all negatives carry the ending is dropped and you add IDE to the end of it. When you are doing the binary ones, when you're combining them and they're just simple ones, positive and the negative, you keep the positive name the same and you drop the ending of the negative one and add IDE to the end of it. For example, sodium chloride. Then we started working with the polyatomic ions, which are the ones that have multiple elements or compounds. Remember that those, if it's written a certain way, you keep it that way. So compounds stay the same. The only thing you are changing is how much of each I have. You cannot change the charges, just how much of each I have. Today, we're going to be working with those same compounds, but these include what we call transition or transitional metals. These are rows 3 through 12. 3 through 12. You'll notice that rows 1 and 2 are easy to distinguish. All of row 1 always carries a charge of positive 1. All of row 2 always carries a charge of positive 2. That's a given. That doesn't change. But starting from row number 3 all the way through 12, that middle block, those can actually carry multiple charges. Multiple charges. Those are called oxidation numbers or oxidation states. So you notice in rows 3 through 12, they can possibly carry multiple charges. Again, those are called oxidation numbers or oxidation states. So we'll look at an example here. Before that, I do want to have you make a mental note that all metal ions are positive. Every time you're dealing with a metal, it always carries a positive charge. Always, always, always carries a positive charge. All metals are positive. It's safe to assume that. Now, we're looking at, for example, let's say iron. Iron, because it can be combined in many ways, can also carry many charges. You'll locate iron on your periodic table. You'll see that it's actually in row number 8. So row number 8 falls in the block of transition metals, which means that it can carry multiple charges. In this instance, you need to be told which charge you are using. The easy part about transition metals when you're dealing with nomenclature is that the charge has to be given to you. You don't guess, it's given to you. What you have to remember is, what do I do with the information that is given to me? So iron with a charge of positive 2, which is an oxidation state of iron, will be written out as a name, iron with a Roman numeral 2. The 2 easily tells me it carries a charge of positive 2. Why is it positive? Because it's a metal, first of all. Why is it 2? Because it has a Roman numeral 2. So these are interchangeable. This is your formula. This is the name. The name is iron 2. The formula is Fe positive 2. You'll notice also iron, if you're looking at your periodic table, row number 8, iron can also carry a charge of positive 3. So if iron has a positive charge of 3, you would write it as iron Roman numeral 3. You have to use Roman numerals. Roman numeral 3. Iron Roman numeral 3. That tells me it carries a charge of positive 3. Let's look at lead, for example. Lead also is a transition metal. That is Pb. You'll notice it has a charge of positive 4, which means that you would write it as lead Roman numeral 4. The name tells me what the charge is. The charge tells me what the name is. You'll be given either or. You cannot guess. If it's just like that, then you cannot combine it with other elements to form compounds. This is pretty simple, simple concept. The charge gives me the name gives me the charge. There are a few you have to pay a special attention to on your periodic table. We'll get to those later on. Right now, we're going to deal with the norm, the general rule of transition metals. So let's look at 2 examples, actually. Let's look at iron chloride. Let's say that the name is given to you, iron chloride. it has a Roman numeral 2. So automatically you're going to assume a metal plus a non-metal. That is an ionic compound. When that's being said, you know that your positive always comes first. Iron is positive because it has a Roman numeral 2. It's a transition metal. You know, iron carries a charge of positive 2 in this instance. Chlorine is in row number 17. We've learned about that before. All of row number 17 carries a negative charge of 1. Now this is a anion, therefore the name has changed. So it goes from chlorine to chloride. We know that, we've understood that concept. So iron 2 chloride is iron metal, chlorine non-metal being combined. So you have a charge of positive 2 for iron, so Fe2. You're adding it to the negative 1 charge of chlorine. Now remember, when you're doing nomenclature and you're doing these compounds, your rule is that you want a net charge of 0, a net charge of 0. So you're going to add the iron 2, positive 2 plus negative 1. That gives me a charge of positive 1. That's incorrect. The charge needs to be 0, as you recall. Chlorine only carries 1. This iron carries 2. So if you think about it, you need twice as much chlorine in order to balance out the charge of the iron. So since you need 2 chlorine, you need twice as much. I've rewritten my arithmetic here, my addition. Positive 2 plus negative 1 plus negative 1, because I'm doing 2 of them, would give me a charge of 0, which is what I want. So since I want twice as much chlorine, my formula for this is FeCl2. I need 2 of chlorine to balance out the charge of the iron. Now I want you to make note, when you are writing the formula for transition metals, you do not put the Roman numeral. The formula never includes the Roman numeral. It does not. The name must include it. You have to put iron 2. If you don't put iron 2, there's no way of knowing how much chlorine you have to match this, because it could be iron 3, it could be iron 4, it could be iron whatever, and you need just as much chlorine to balance that out. So you have to put it in the name, but in the formula you do not. So you're probably asking why or how is it that you'll know which iron it is then? You can easily tell by the negative 1. If you have 2 of the negatives, you need 2 of the positives. So you know by looking at this, oh, this is iron 2, without having to write it out. You know this is iron 2 because it's chlorine twice as much of the negative. So the math equals 0. Once again, you don't put the Roman numeral in the formula. In the name you do, in the formula you don't. It's the same concept as before. You just want a charge of 0. Okay, let's look at another example. Let's look at cobalt. Cobalt is also a transition metal. You'll notice cobalt is in row number 9, which falls in the category of transition metals. So because cobalt is a metal, we know it has a oxidation state of 3 in this instance, and we know that it carries a charge of positive 3. Oxide is obviously an ion of oxygen. Oxygen is in row number 16, and we know that row number 16 carries a charge of negative 2. So we have positive, negative, metal, non-metal. This is an ionic compound. We know that. We're going to combine them. So cobalt automatically carries a charge of positive 3 because of the Roman numeral. Oxygen carries a charge of negative 2 because of its location on the periodic table, because of the row number 16. So you have a positive 3 and a negative 2. It's automatically safe to assume, you can do simple math in your head, they're not going to add up to 0. Positive 3 plus negative 2 is going to give me positive 1. So I'm going to have to do the same thing as this one. Now for these, since both of them will not add up to 0, you're going to have to change both sides. You're going to have to change the cobalt, and you're going to have to change the oxygen as well. So if by the way, you don't have decimals or fractions when it comes to this. They have to be whole numbers. So I can't make the 2 into a 3, and I can't make the 3 into a 2, obviously. So I need to find which number can they both be factored into, the smallest one. That would be 6, simple math. So I'm going to make both sides a 6. So if my cobalt already carries a charge of positive 3, and I need to make it a 6, I need 2 of the cobalt. And if my oxygen already carries a charge of 2 and I need 6, I need 3 of the oxygen. So I need twice as much of the cobalt, so 2 times the 3, and I need 3 times as much of the oxygen, 3 times 2. So 2 times 3 is 6, 3 times 2 is 6, positive 6 plus negative 6 is going to give me a 0. 6 plus negative 6 is a 0. So if I'm going to write this formula out, it's going to be cobalt 2, oxide 3. Cobalt 2, oxide 3. I want you to pay attention to this. This is very important. It's a mistake you might want to have the habit of getting out of. The subscript is not telling me the charge. This does not mean cobalt has a charge of 2. It's telling me how much of the cobalt I have. The charge is given to me either in the name or based on my negative. In this instance, when I'm working with transition metals, you would look to the negative side, to your anion side, to tell me what charge the positive has. Because oxygen, as you know, always carries a single charge. It never changes. So if oxygen always carries a charge of -2 and I have 3 times as much, 2 times 3 is 6, that automatically means that this side has to have 6. I have twice as much, so my charge has to be 3. Again, it's simple math. You have to just do it over and over and practice it. The subscript is never going to tell me what my charge is. My subscript tells me how much of each I have. So don't make the mistake of saying, oh, my cobalt carries a charge of 2. No, you have 2 of the cobalt atoms. You still have to figure out the charge in order to see what this side looks like. You would look at the negative side in order to do so. The same thing with iron. You know that this iron does not carry a charge of +1 because of the subscript. You know because of the chlorine that this side is +2. Same thing for this side. Look on your negative side to see what your positive side charge needs to be. These are 2 examples of transition metal ionic compounds. Once again, the only difference is that you're adding Roman numerals in order to be able to see your charge. You have to be given. So either the name is given to you specifically or the formula. When you look at a formula with transition metals, you automatically look to your negative side in order to do so once again. So these are oxidation states. Is